Thank you, Leland. I'm going to be talking about something that's very, very similar. And in fact, Joel and I are collaborating on various aspects of it. I'm doing wideband autocorrelation radiometry. And the idea behind this technology is to measure the layer thicknesses, and in particular the one that gets regenerated every year is snow and ice, and that helps out a lot with being able to make good measurements of it. The stuff I'm going to be presenting, pretty much all the photographs and the data and whatnot, really belongs to Mohammed Musavi, who's right here. And I'm giving a little bit of a preview of his defense in 2 weeks. So if you get this, you go to his defense and you're going to get more detail in the dirt. The other person I want to point out is Tony England, who actually came up with the concept behind this. But it's really his work. I'm just going to be covering basically the simple measurement concepts that we're trying to do, how we came up with the instruments that we've got, and how it's calibrated, and all of it's a little bit weird. It's quite different. I'm having a lot of fun because it's not traditional radiometry. Some initial results and some conclusions where we're going with it all. The reason people want to know about snow is because it's a source of drinking water, and water for all sorts of uses, agriculture, all over the globe. Not so much around here, but certainly in you think of California and the Sierra Nevada. That's where California gets its water from. You should know how much water you're going to get if it's on the ground, but it's actually really hard to measure. And even just physically measuring it in one location, 50 meters away, it's different, different depth. And on top of it all, the climate's changing. And so we're looking at wideband autocorrelation radiometry, and I abbreviate it as WiBAR. It has the usual remote sensing pluses. It's microwave, so it penetrates the atmosphere very easily, goes through clouds. This is a passive technique, not a radar. And I'm not even I'm really measuring truly passively, measuring the Planck emission, not a scattered source from somebody else. And therefore it's low power, which means it has a better likelihood of getting into space, because low power means it's cheaper. And the way I'm implementing it, it's sensitive to the layered structures, and because of that, it's beautiful for doing these layer measurements, and it really doesn't respond to very much else, which is kind of a weakness, but in this case, it's a strength. The way we do the measurements today is through a method called differential scatter darkening. We take 2 microwave radiometers at sufficiently different wavelengths. These are the 2 traditional channels that are used, usually the V polarization. If a snowpack is dry, it does not emit, it does not absorb, but it does scatter. And how strongly it scatters depends on how big the characteristic sizes of the particles are relative to the wavelength of the emission that's coming in from underneath the snowpack. And so at a longer wavelength, you get a bit less scatter darkening than you get at a shorter wavelength. And as the snow depth increases, what would be pretty close in brightness for the bare ground, you start seeing a decrease in the brightness due to the scatter darkening, and the shorter the wavelength, the more scatter darkening you get. And so the retrieval algorithms are basically something along these lines. You're looking at the difference in the brightness temperature that's measured, and you multiply it by some kind of scaling factor. That's not a wave number, that's a coefficient, and you achieve the snow depth. Now, let me say this nicely. We've been making progress on understanding what that coefficient is for the last 30 years. But it's still, the way in which it's determined is really to get out there and measure the snow depth in a lot of places, measure the brightness temperatures, and do a regression, which works great until the climate changes. Then you got to do it again. So this is not a completely satisfactory, even though it's been out there for 30 years as a way of doing things. It doesn't work in the mountains because it's not really a linear process in terms of what this coefficient is. It depends on the grain size. Grain sizes are different in different places, even in the valleys and things like that. So I'm going with something a little bit different. We're looking at, again, the Planck emission coming from underneath the snowpack. It will transit the snowpack and head off towards what hopefully is your radiometer to capture the signal. But if you're doing it at sufficiently long wavelength, you'll really start not seeing the scattering, the volume scattering at all. And so what you're not measuring is the accumulation of volume scattering. What you're seeing are the interfaces at the top and the bottom. And you see a reflection off of this top surface, a reflection off the bottom surface, and there'll be, in addition to this direct transit of the snowpack, a copy of this noise signal that is attenuated because these things have finite reflectivities that are some relatively small, and time lagged because the transit time is a bit longer. And if we take a look at what will happen is that we autocorrelate the signal that comes in. You'll see a very strong response at zero lag of the direct ray and the delayed ray, for that matter, with itself. But at some finite lag time, the delayed ray will be correlated with the direct ray, and that will yield a measure of how long this thing has been traveling to transit the path in both directions. And you can work out what that is. It's basically the vertical component of the wave number integrated over the depth. And it goes back and forth, so there's a factor of 2, is related to the electrical length that the delay time kicks out. Turns out if you assume a refractive index mixing model for this dielectric constant, it's not the best model, but it produces a simple result. What you can find out is that the delay is essentially proportional to the snow depth times a couple of constants of nature times what is called the snow water equivalent, which is how much water you get when the snow melts. Those constants all work out to just one number, and so it's essentially like a sum of these two, especially at nadir. The snow depth plus the SWE is essentially how long things are delayed. And then Mohammed has actually worked out the fact that this is at nadir. If you do it at grazing, you might even be able to start separating these two out because you start seeing different things going on. So there is some way of measuring things. It's not perfect, but snow depth and SWE are the two parameters that are highly correlated with each other. Right? We're at least measuring the sum of the two. In order for this stuff to work, the slab that we're looking at can't be absorbing, which means it's got to be dry. We're trying to minimize the scattering at the surfaces and within the volume itself. This is still true for the old microwave remote sensing approach using scatter darkening. This is completely different. This is the thing that we're trying, essentially the assumption that we're violating, the second one. And then if we go for a long enough wavelength, we achieve minimal volume scattering, and we also can start making those surfaces smooth with respect to the wavelength. And then electromagnetically distinct as you go across the boundary is the other thing to go for. What this implies is that H-pole is what you want to use. So again, just like from the scatter darkening approach where you want to use V-pole, you want to actually minimize the effects of the interfaces. Here I'm really amplifying the effects of the interfaces. And this does imply that we need to be working at a really long wavelength. And snow is kind of tough. It's this distinct vertically is sometimes doesn't hold real well for like the ground to the snowpack itself. Sometimes they're pretty close to each other. But there is another naturally layered surface layer that actually satisfies all of this stuff really nicely. Ice, freshwater ice, really nice surfaces, smooth surfaces on the top and the bottom. And in fact, very distinct dielectric constants of the 3 layers. And we can go to much higher frequencies where there's a lot of bandwidth available for us to use and a lot less RFI also. And so I'm mostly going to be talking about measurements of ice because that allows us to really start proving how this technique works. So for ice, the other thing that's nice about it is that there's no variation in the pack. It's actually just really constant at the dielectric constant of ice. And the relationship becomes a relatively simple little thing where you're directly proportional to the ice thickness with a little bit of an angular dependence that's attached to it. How would we do this? The straight ahead concept would basically just put a front end of a radiometer, basically pull in your signal, amplify it, and then perform some kind of autocorrelation on it. Notice that I don't really care what the power is, and I'm not really going for that. One way to do the autocorrelation is to split the signal and have a variable delay on one path before I autocorrelate them together. Turns out that's a bit of a pain in the butt. It seems like a nice idea, but a variable delay path is actually relatively tricky to achieve. One thing that is possible, of course, is if you can do like Joel's doing and pull the data into the digital domain and then do it digitally. That's one thing that we're working on, and actually 2 of my students are working on that right now. Miriam is working on the analog portions of it. Engineer in Sperl, Steve Rogacki, is working on the hardware end of the digital, and Puneeth, I think I saw Puneeth come in here at one point, is working on the firmware for the actual autocorrelation algorithm. But there's another way to do it, and that's basically, this is a poor man's copy of ultra-wideband software-defined radiometer. Take your antenna, the regular radiometer front end, and I'm just going to use a spectrum analyzer as a receiver. Pull the data off of it. What I will have is a frequency, power spectral density as a function of frequency. And what I would expect in my signal is that there's going to be some kind of oscillation going on, where at some wavelengths, that extra path is going to do constructive interference and give me higher power, and at some frequencies, it's going to be destructive interference and produce lower power. If I find this kind of pattern, I can do an inverse Fourier transform on my spectrum to get an autocorrelation function. That just comes from signal processing. And so that's what we tried to do. The other thing about building the hardware is, like I said, I'm not making measurements of power. This is not a traditional radiometer. I don't really care what the brightness really is, which is really nice because trying to make really clean absolute power measurements means you really have to be careful with your radiometer, and there's a whole host of techniques to try to control the gain of the radiometer chain. So that you're not seeing variations of your instrument instead of variations of your target. Don't really need that here. So that's a big bonus. But the problem is you need a lot of bandwidth in order to be able to do the resolution of all this, because these peaks in the autocorrelation domain, their width is related to the reciprocal of the bandwidth of the instrument, or at least the frequency span of the instrument. And then for the things that we're looking at, snow that tends to pile up in increments of 10 centimeters or so, you need a couple of gigahertz of bandwidth. That's a lot of bandwidth, especially down at 1 gigahertz. First prototype was literally that block diagram. You had an antenna, had an amplifier, had a spectrum analyzer. We strapped it onto the antenna, and off we went. This little box here is for holding 9-volt batteries that powered the amplifier. We were ready to go. And so that's what we did. It works out great. But it doesn't last very long. The 9-volt battery, we went through lots of 9-volt batteries. This thing is really massively heavy. It doesn't last all day. It does eventually fall over because it's pretty unwieldy, and we broke it. We did get some great data out of it, though. So the next round, we tried to minimize the weight and lengthen the runtime. And for this, what we found was a commercially available spectrum analyzer that was actually powered by USB, really nice. But it only goes up to about 4 gigahertz, but that's still plenty of bandwidth. So all we need to do is then down convert our RF signal down to an IF stage, and we're ready to start running. And in this case, even more than that, we now actually have an onboard computer actually controlling the whole thing through a Raspberry Pi. Same antenna, well, actually, it's a different serial number, but the first one was broken, but the same model number, and we're off to go to the races. We've also built some other ones at lower frequencies, looking specifically at the snow. There is an L-band one right here and an S-band instrument right there that together cover about the same frequency band as ultra-wideband radiometer. This was deployed up at the biostation up at the tip of the mitt of Michigan, where we had a decent enough snow cover to be able to see some signal, but we didn't actually pick up any, and I think it was because things were a little bit too warm, and so the snow was a little too wet. So actually, we're trying again. We've got this instrument actually deployed up at, the truck is deployed at the Keweenaw Research Center in Keweenaw right now, where things tend to be deep snow and drier, and we'll see what we can do. And actually, a version of ultra-wideband radiometer from Joel is actually going to join us up there, so we'll see what we can get. It's pretty much the same thing on the inside. It's a spectrum analyzer, same model of spectrum analyzer inside. This is the back end of the antenna with the receiver mounted on it. For the heck of it, to see if I can lower the noise floor of my autocorrelation function down, I do have the capacity to do thermal control, and we'll see what effects thermal control actually does and see if things improve. The shortcut might be just to use your instrument because you'll have it. We'll see. What we get when we actually make measurements, it is still the traditional radiometer equation. The power that you actually get in a narrow bandwidth when we sweep it over frequency is going to be the Boltzmann's constant times the system temperature times that bandwidth times the gain of the thing, the gain of the gain chain. The system temperature itself is composed of the emissivity of the target times the temperature of the target plus whatever noise the receiver's adding. And if we look at this, we've got 3 different parameters that depend on frequency, and then so that's what I've got to eliminate and take care of. What I'm doing is measuring the target that I'm interested in. I'm going to measure 2 others that are at different brightness temperatures but are having spectrally flat emissivity. The sky is one. An absorber or a match load is another. And what you come up with are some really hideous looking power spectra, but that's okay. If you apply the formula, what you end up getting is an extraction of something like an emissivity. Sometimes we actually get emissivities greater than 1 because the electronic power, the gain of our electronics may have drifted a bit, but that's okay. I just want to get the variations with frequency, and I can actually extract it. And so that was an example of lake ice, where we can actually see the oscillations going on between the ice relative to, say, the matched load. Take the inverse Fourier transform in order to come up with the autocorrelation function, and something like this comes out to a really nice clean signal. There's a nice peak that happens, very distinct. That's at around 7 nanoseconds. If you plug in the values for the incidence angle and the dielectric constant of the ice, you end up coming up with an ice thickness of about 59 centimeters, which corresponds quite well to the ground truth when we actually we're done with the experiment, and we augured a hole in the ice and then measured how thick it was. When you measure it over many different incidence angles, this was actually a result of our very first the instrument with a very heavy spectrum analyzer attached to it, and measure it over incidence angles. You can also start to see the angular incidence angle dependence in the expected lag time. It's the longest lag that happens right at nadir, and then as the angle goes up, you start getting a little bit more, getting less lag for the same ice thickness. But it works out pretty far. This one, we see a little bit of a bias. There's actually 3 curves on here. The blue dashed line is actually the curve that would correspond to the ground truth that we measured, but we suspect that the ground truth is itself is a little bit biased on the shallow side. Because of the technique we use where we busted away the ice. The other piece is that we have since made measurements beyond this to 70 degrees, and I think have we gone as far as 80 degrees to get good results out of the back of it? 72, okay. So we can get at least this far. Our theoretical calculations say we can get around 80-ish. And actually, a lot of things work out a lot nicer at those incidence angles. You get a better, clearer signal and noise ratio than you usually do over here. If we take a look at bare ice and this relationship which gives a prediction of the delay. If we plug in the measurement of the ground truth, we find that it's linear. It's doing what it's supposed to do. It's depending on the thickness of that slab layer. The RMSE of like 1/10 of a nanosecond, whether it's covered with snow or whether it's bare ice, is saying that we're getting within 2 centimeters each time of the right ice thickness. Over ranges of ice thicknesses, quite a bit up there. It also does work for snow. We've got some limited measurements of snow. At these lower frequencies, we do see RFI instances, some spikes of RFI. This is a result where we did not even try to eliminate that RFI. We just left the spectrum alone and just ran with it. What it does is it brings the noise floor up when you have RFI, because it's a very narrow RFI in frequency, turns into very broad in the autocorrelation function domain. But you can still pull out some measurements of the snow thickness. One thing we're looking at to see if there's something that this technique really provides beyond what you can get with differential scatter darkening is we know about how wide these peaks are supposed to be. It's based on the bandwidth, or at least the frequency span of the instrument. If you see stuff that is a little bit more than that, are we starting to see things within the footprint, some variations? And some evidence of that actually came out, and this was this past winter up at Douglas Lake, again at the University of Michigan's property up on the northern lower Michigan. We actually went out into the field, made a measurement, and we came back to our little cabin that's still not doing things in real time, but is doing it in, we post-process it pretty quickly. We found a measurement where we had 2 peaks instead of just 1. And it's like, whoa, what's going on here? This is, did we do something wrong? What we did figure out is that maybe what we're seeing is a transition in the ice itself having 2 distinct thicknesses, which is indicating that, yeah, this thing is actually making measurements of stuff that's beyond just happening in a single footprint. This is the location where that measurement took place. We were actually measuring it at 70 degrees from a tripod mounted here looking out this way. And it looks like it's actually hard to find, but this is the next day. We came back out and we started taking pictures because we knew they had something here. We could find it because what's not in the picture is that there's also a whole bunch of ice fishing shanties all over the place. So you can actually triangulate where you were pretty well. On top of it, this thing is powered by a motorcycle battery, and it was sunny the day previous, so there was a perfectly formed tiny little rectangle on the ice showing exactly where we were. So we could come back. And we did some measurements like this, just pointing straight down at nadir, having the smallest possible footprint to make the measurements. Those 2 peaks corresponded to 38.5 and 42 centimeters. And the individual measurements at these locations, now that's done at nadir, so there's an incidence angular dependence, so the time lags are different, but the thickness that corresponds to it is about 41 centimeters and 39 centimeters, indicating that there is a transition happening where there's thicker ice over here to thinner ice over there. And we didn't really notice it until after the fact, but we were also making a measurement right where this nice dark clear ice goes into a cloudy zone along here, and then it's clear ice again over here. So we're surmising that what happened is the ice was freezing up earlier in the season, and then a warm spell or windy spell came, broke up the ice back to here before it got colder and started freezing out again. And so we have a transition of the ice thickness at that particular point. So this is kind of like really exciting because it's indicating that it's a microwave radiometer. It's going to have a huge footprint, no matter what. But at least you can see some more stuff than just one single average number within your footprint. You can actually start seeing that there's different values within your footprint, which means that there may be some deconvolution possibilities. So we're really excited about that. Yeah, this is putting me at a pretty good time to end here. So the objective is to measure the vertical extent of snow and ice packs. We're using something that is really insensitive to anything other than that. It's basically coherent microwave radiometry. What the heck is that? It has the benefits of microwave passive operations, being low power and all-weather capability. This is a little bit different. For measuring these slab thicknesses, you don't need to calibrate your algorithm. You just need to calibrate your instrument, and even the instrument calibration isn't that onerous. And since it's a linear dependence of the thickness to the signal that you actually see, variability within your measurement contains information about variability of your target. The challenges, of course, are that it will always have a very large footprint, but hopefully this can help mitigate that. And the other is that you'll always be wide open in bandwidth, and so you'll be always susceptible to some RFI. Fortunately, RFI, it raises your noise floor. It doesn't completely destroy your measurement, unlike in traditional radiometry. So this is the kind of stuff that I'm exploring at the extreme other end of the technology readiness level spectrum, from things like what Chris Ruff is doing, where he's flying satellite missions. I'm trying to come up with techniques at the very beginning end of it all. Anyway, so thank you very much.
Okay, any questions?
Was that a raised hand, Chris, or? Okay.
So do you see this working up there?
Maybe. It depends on how up there you go. And that's certainly the reason why I'm trying to continue to explore this. Getting up onto airplanes, yes, I can see this working really well in quite a few circumstances. How well it works there will tell me how well it will go to the next level in going into orbit.
I mean, other than the footprint size, what else doesn't scale well?
It's the footprint that's really the big deal. The other is the bigger the footprint, of course, the more RFI you're picking up too. I mean, those two together really play together, but it's the footprint that's the killer.
I mean, if you notch out the spikes, that doesn't really degrade the autocorrelation.
That's the hope. That's the plan. Hopefully, Miriam will help me show that.
Just want to understand the fundamental principles. So you have your and then so that's coming from some thermal source.
Thermal source underneath. It's actually, we even know the temperature for lake ice.
And the reflected rate path interferes with that.
Yep, and that's what we're looking at.
And then you're looking at just you're looking at time delay between those.
Yep. Yep.
Is the direct path and the reflected path, are they going to be coherent enough you can get a phase difference between them?
In this particular case, if you calculate there'll be a specific time lag.
Right.
And then the actual phase difference between these two for this geometry, it will be 180 degrees. It'll actually be an inverted copy of the signal, and that's because we're reflecting here from.
Oh, I see what you're right, because the path length is going to be exactly twice the.
Yeah.
Okay.
The 180 degrees comes about because you're going from high dielectric to low dielectric here, and going from low dielectric to high dielectric there. So the reflection coefficients at these two are flipped in sign.
So whatever your thickness is, it's always going to be exactly half a size.
Exact copy, but a lag, and how big the lag is tells you how thick it
But
was.
they are, if I look at those are coherent.
Yeah.
So, okay.
Yeah, they are. Yeah.
No, that's fascinating.
It's. Thank you.
More questions? All right.
Cool. All right. Sure.